Okay, well, we are recording and okay. My name is Carla Keene and I want to welcome everyone to our August edition of Slow Your Roll, Plan Before You Plant. I am based in Clarksville, Montgomery County, Tennessee. And our speaker today is a gentleman from Florida A&M University. Dr. Magee is a professor there at Florida A&M, and we actually got to meet in person this past week at the 1890s Extension Conference. So that was good to meet face to face before this meeting. Today, Dr. Magee is going to talk to us about his post-harvest invention for fruit and vegetable cooling and storage. And so I will turn it over to Dr. Magee.
Well, good afternoon. Let me apologize for being late. I was thinking it was starting at 12:30 rather than 1 o'clock. Well, 1 o'clock my time.
Yeah.
Your time. But I'm pleased having an opportunity to talk to you about the post-harvest invention.
Okay, you probably need to go ahead and start your slideshow because we're seeing your notes on the side.
Well,
just start your slideshow from beginning.
I want to first talk about the precursor, an invention that I did about 32 years ago, 33 years ago, dealing with pre-cooling fruits and vegetables. And let's go. So post-harvest invention for fruits and vegetables. We know, at least I don't have to tell you, if you're in the horticulture industry, we know that all vegetables continue to lose water after they are harvested. That's a known fact. And so let me see, where are we?
Dr. Magee, I think you need to click on slideshow and from beginning, and that way we can see your full slide rather than the notes and the pictures.
Okay, I'm having some problem with my technology.
Okay.
There
you go.
Okay. Let's try this.
Yeah, you're good now. We can see just your
I'm good now.
You're good now. All right.
All right, yeah.
Thank
you. Okay. We know that all vegetables, once you harvest them, they're gonna continue to lose water. And that's a bad thing. We want them to retain as much water as possible. But some of the ways in which we know fruits and vegetables lose water after post-harvest, we know the number one way is moisture content and temperature of the air in contact with the vegetables will cause them to lose water. Hold on just a moment. Let me get rid of the pictures on the side. Okay. So we all also know that vegetables gonna lose water if they are subjected to air movement, which we call convective evaporation. We know if you're blowing water over the leaves or the surface of a fruit or vegetable, that it's going to evaporate the water and they're going to continue to lose water. And the higher the temperature difference is between the surface temperature and the temperature of the product, the greater your moisture loss is going to be. I think we also know that atmospheric pressure can have an impact on water loss. We know if you, like in vacuum cooling for vegetables, especially like lettuce and some of the other vegetables, we use vacuum cooling. And vacuum cooling, basically all it's doing is just lowering the atmospheric temperature around that particular product. the lower the atmospheric temperature surrounding the product, the greater your loss of water is going to be. But we use it, like saying lettuce, especially head lettuce, it works better. It works a lot better than hydro cooling. In other words, different than cold water, running cold water over the lettuce. So vacuum cooling worked very well in leafy vegetables and some other vegetables as well. But these are there are other ways in which fruits and vegetables lose water, but these are the main 3 ways that I'm dealing with as far as the 2 inventions that we're going to be talking about today. So the first patent that I got in 1989 was a special container for fruits and vegetable pre-cooling and shipping and storage container. It was a fruits and vegetable pre-cooling, shipping and storage container. If I can go back, didn't want to go back that far. So my first invention, this invention was done in 1989. Basically, it's a styrofoam container. In other words, a good insulator. Styrofoam is a very good insulator. And the basic concept was that you would, in the lid of the container, you would insert an ice cavity. A cavity, you fill it up with ice. This is a perforated cavity, and naturally you fill it up with water, you freeze it. It's a simple concept. When you harvest the vegetables, you put them in the container. As the ice melts, the water is going to drip down on the product within the container. Okay, and it's going to certainly lower the temperature because the surface of the product is going to be at a much cooler temperature than the inside of the product. So not only are we removing heat by convection, we also removing heat. We have a heat loss from the product due to convection. So, due to conduction, okay? So we have conduction and convection, both heat. These are the 2 types of heat losses that we will be dealing with. So now, the unique thing about this version of the container, you're going to insert this lid, which is what you see, the number 20 right here, and you got the perforated holes below, perforated hole. Naturally, you got to have an inlet to put the water in. You're gonna freeze this cavity with ice, insert it into the lid. Now, 32. If you look at item 32 here, at item 32, this is just an inlet door. You can stack these containers on top of each other, stack them on top of each other. As the water drips down on the products inside of the chamber, it's gonna go down. Okay, it's gonna go through the surface of the next chamber. We have a hole in the, which you don't see in this version, but we'll get to the next version. So water is going to go from, so we're going to have a cascading effect. As the water melts in the top container, it's going to go down to it's going to go into the container beneath it, okay, through an inlet hole, and the water is going to be distributed throughout the vegetable in the lower container. You'll see it better when we come to the next version. And certainly you got drain holes in the bottom, and you got the channels in the top of the lid, okay? And it's going to be an opening in the channel, in the channels that you see in the top of the lid, on the side of the lid, and the water will go from one container, the cold water from one container to the next container. And then you have like a drain pan, a tank or something at the bottom that's going to collect all the water, and with a recirculation pump, you can bring it back to the very top. Okay, this is the next slide. Basically what I was just talking about now. In this slide, you see the channels that you see on the side, number 64, okay? The lid is represent number 56. Now, in this particular version of it, you have a manifold system built into the top of the lid. You have a manifold in the top of the lid. So, and you have an opening in the top here, down here where you see number 54 on the bottom container, that is the opening. So as the water, and these are the drain holes that you see in the second container. In this second container, when the water melts, it's gonna come through the drain hose, and it's gonna go down to the channels here. It's gonna go down to the channels that we have on top and down the side. Now, if you have a particular, if you got different types of vegetables, okay, and you may not want water to go on, to fall on the surface of those vegetables, you would just simply close the inlet hole, close this inlet hole. Now the channel, the water is going to divert down the channels, down the side, and then it will go to the next container below this bottom container. Okay, but if you want to divert water away from one type of vegetable, let's say if you got blueberries, okay, and you may not want the water to touch those blueberries, so you don't want to have leaching. So you would just simply close off the inlet hole, and then the water will go down to the next container where you may have corn, sweet corn, or tomatoes, or whatever you might have in, okay? So, and with the manifold system, so when the water will come into the inlet down here at the bottom, it's gonna go inside, it's gonna go in the manifold system, and you're gonna have a distribution. You're gonna be showering the product with water. And again, the water is gonna go down to a collection tank with a recirculation pump, and just with a recirculation pump, now you can bring the water back to the top, and the process will continue. In your recirculation tank, you're gonna have ice in the tank. So in other words, you're gonna be bringing back, you're gonna be recirculating like 35 degree temperature water at all times throughout the whole system. This is what we're talking about. If we got this container at the top, this reservoir of cold water, okay? It's gonna come into the first container, and you see the open area, this cross section of view, where you see the opening into the top of the lid, into your manifold system. And the manifold system, certainly, the laterals in the manifold system, they got small holes in it. So you're gonna continue to shower water on the vegetables below. Then it's gonna drain down through the drain holes at the bottom, go into the opening for the next container below, and it's gonna shower water. We're gonna come down here to this water collection tank. And with a circulation pump, we're gonna pump the water back up to the very top, and we're gonna just keep recycling the water throughout the system. So this is the gist of the first invention. So this is the precursor to the next invention, to the osmotic chamber, okay? So the osmotic system for the maintenance of perishable items, okay? The patent was awarded last December. This is showing the system. The outer boundary just represent, the walls of a walk-in cooler, okay? So we can push the whole system. In the osmotic system, we can push the whole system inside of a walk-in cooler. The components that make up the system. The components that will make up the system: air compressor, ozone generator. We got a reservoir for water or saline solution, and we have a humidifier. These are the basic components that makes up this components that make up the system. Now, let's go. Typically, the way we handle vegetable, this is just showing you a cross-sectional view for the osmotic chamber, cross-sectional view with the osmotic chamber. Normally, the way we handle these steps may not be, all the steps may not be necessary, and we don't have to take them exactly in this particular order. But in the real world, what do? It's dealing with vegetables, especially leafy vegetables. Time you harvest, let's say for instance, if you have collard greens, since we live in the South and stuff, with any vegetable, whether sweet corns or greens or whatever it might be, whatever type of vegetable, your goal is the first thing you would like to achieve is to reduce the field heat as soon as possible. So you want to start the pre-cooling process as soon as possible. So pre-cooling, pre-cooling, your steps that you normally will go in, the steps that you normally would take in this system, you want to start out by pre-cooling the perishable item to a temperature between 1 and 3 degrees C. In other words, in degrees Fahrenheit, about 35, anywhere from 33 to 35 degrees Fahrenheit is the ideal temperature that you want to get your vegetable down to as soon as possible. It depends on what type of vegetable you're working with. But the bottom line is you want to get the field heat out of the vegetable as soon as possible. So in combination with the first invention I had, that container, the container where we have the ice wall, I mean the cavity of ice, the layup ice in the lid. As you harvest the vegetables in the field, you can put them directly in that container, okay? Because you got this ice cavity with the frozen ice, and it's gonna start the pre-cooling processes. At the time you harvest them, cut them from the stalk, it's gonna start the pre-cooling process. Now, the next step, providing a refrigeration system and placing the perishable items within the pressure chamber under positive pressure. If we go back, if we go back here, we got the compressor, the air compressor here. This would be the chamber would be airtight. Okay. Now, eventually, when you first put it in there, you don't bring the pressure up. You can have it at regular atmospheric pressure, but eventually you want to raise the pressure. So your next step, you harvest the vegetables. You harvest the vegetable, you put them in your container, you put them into the chamber. Then you want to wet the vegetables, the surface of the vegetables, with a saline solution, okay? Meaning, I don't know, maybe 95% fresh water, 5% salt in the water. You want to wet it with a saline solution. Now we can do that. We can either dip the vegetables in the saline solution, or we can use an electrostatic sprayer in order to apply the saline solution to the surface of the vegetables. But anyway, shortly after you do that, as quick as possible, you want to dry that, you want to dry the surface of the vegetables with that saline solution. So now you got a film of saline solution on the surface of the vegetables, And we can use the air compressor in order to dry the vegetable as well. Okay, so so now we are air drying the saline solution sprayed on the surface of the perishable item and saturating the chamber with ozone gas. If we go back, we know that what ozone gas is a bactericide. We can use ozone in order to kill bacteria that might be on the surface. Not only will kill bacteria, E. coli, it can also kill E. coli as well. Okay, so now after we have air dried the saline solution on the vegetables, we want to saturate the chamber with fresh water, okay? Now, we know with the saline solution on the surface of the vegetables, now you're gonna have what? This is when osmosis is gonna take place. If you surround those vegetables with water molecules with a higher chemical potential than the saline solution, we know from osmosis, water is going to be drawn into the surface of that vegetable. It's going to come inside the pores, and then it's going to get into the cells of the vegetables, and it's going to keep the vegetable, the hydrostatic pressure is going to build up, and your vegetables is going to continue to be rich. So we won't have any wilting to take place. The vegetable will still be nice and firm due to the hydrostatic pressure that the osmosis is going to cause during the osmotic process. Now, so operating the humidifiers and and increasing the relative humidity of the system to about 95 to 100%. And we using 95 to 100% because almost all vegetable, the moisture content is going to be less than 95%. Okay, we know the moisture content almost any kind of fruits or vegetable is going to range anywhere from 80% all the way up to 95%. Some leafy lettuce might get up, the moisture content might be as high as 95% or 94%. But if the relative humidity of the air, if the water vapor in the air is higher than the water vapor, than the water inside of the vegetable, we know that this due to osmosis, it's going to pull water, the water vapor is going to pull water inside the pores of the leaves, and it's going to build up the moisture content, build up the water content in the cells in the vegetables. Now, I said earlier in talking about the first invention or any case, when vegetables are surrounded at a lower pressure, we said earlier that you're going to have a greater moisture loss. They'll lose moisture much faster. Now, in combination, the reason why we want to raise the atmospheric pressure inside of the chamber, we want to raise it above regular atmospheric pressure, which regular pressure is 14.7 pounds per square inch. So if we raise the pressure to above 15 to 16 pounds per square inch, we expect with the combination of osmosis and the positive pressure, it's going to force water vapor to go inside, water molecule to go into the cells of the product. And it's going to keep the product, again, nice and firm and rigid, okay? In other words, you won't have a wilted product. We know wilting normally shows up when you have a 10% greater, 10% or greater moisture loss. In most vegetables, if they lose 10% of the weight, you can visibly see that wilting has taken place. And you know, no matter how nutritious though that product, those greens or whatever, might be if they are wilted, the consumers, they simply not gonna buy those vegetables. But from a nutrition standpoint, all the nutrients are still there, but just from an appearance standpoint, folks not gonna buy wilted vegetables. If you walk into a supermarket and you have a bunch of greens or whatever, asparagus or whatever you may be, if they look limpy and wilted, you might pick them up, but you're gonna put them back down. You're not gonna buy them, okay? But anyway, so with the combination of the osmosis and the positive pressure and the positive pressure, it is going to prevent the vegetable from becoming wilted. And in the next step, placing the rehydration system within a cooler, lowering the temperature to between 1 and 3 degrees C. At most supermarkets, those coolers, those walk-in coolers, they typically is going to keep them around 35 degrees F or around 2 degrees C. Within this system, you can include an ultraviolet, UV light located inside of the chamber. UV light will also, as you know, will also kill bacteria as well. And it will sanitize that whole system, your whole system. We can use UV light to sanitize it and sanitize the products that within the system, okay? And in the last step, operating the cooler at the same temperature and pressure and relative humidity as the chamber. If you got the cooler and the chamber at the same temperature, you won't have any heat flow, okay? If the cooler and the chamber both are at the same pressure, okay? If they're at the same pressure, you wouldn't have moisture flowing in and out of the cell. But the pressure inside of the chamber is at a higher pressure. So the water vapor is going to be forced to go through the surface, go inside the tissue of the particular product that's in the system. So that's another reason we want to have a slightly higher atmospheric pressure surrounding the vegetable. Now, with this system, with the combination of the saline solution, when you use electrostatic sprayers to attach water molecules to the surface of the vegetables, electrostatic molecules, like I think we all have had the experience of static shock when you walk on a carpet and you touch that doorknob and it almost knock you down. So if you got any worms or insects within the vegetables on the surface, or for that matter, inside of the vegetable, the electrostatic current, the voltage, that high voltage is going to kill those organisms. So that's one way, okay? And the saline solution, you know, will kill bacteria. I think we all have experienced, we see it every day. If you buy a jar of pickles, as long as those pickles are under that, under the water, below the water, not water, below the saline solution, that's a brine solution. As long as they are below, you don't have to refrigerate those pickles. You can leave that jar of pickles on the countertop for 6 months and those pickles are still good when you come back. It's because, and the same thing as they do, even at the fish market, okay, sometimes, well, you're at the big fish market, they do what? They put salt over the fish in order to kill the bacteria, which is gonna give them a longer shelf life. Okay, when they bring in the fresh fish from the ocean or wherever they might be bringing them from. So you have about 3 different ways that you can destroy bacteria and also kill worms and insects in this system. The electrostatic sprayer, the electrostatic, when you apply the molecules electrostatically, okay, the molecules of the saline solution, That's gonna kill any worms or any insect. The saline solution, when bacteria tries to attach itself to the surface of the vegetable, what's gonna happen? The salt that's in that saline solution, it's gonna pull water out of the cells of the bacteria, and they're going to die. It's gonna kill. They're going to die. The ozone gas is also a bactericide. So we have about 30, and plus the fact, ozone gas, the water could be slightly chlorinated as well. So you have about 4 methods that you can use to kill bacteria, insects, and worms that might be in your particular product. Now, if the vegetable is sanitized and the whole system is sanitized, you don't, and you lower the temperature, what you have done, if the temperature is 35 degrees, we know what? We're gonna lower the respiration process. And we pour water into to the pores. Theoretically, you ought to be able to keep those vegetables for months rather than 8 to 10 days as they normally do, because you won't have any decay because you have killed all the bacteria, and hopefully, not hopefully, you won't have any fungus to grow on the vegetables because of the what? Ozone, and if it's chlorinated water, and if you use chlorinated water, that's gonna kill bacteria and fungus on the vegetable as well. So you theoretically, you should be able to keep it, like I said, for months rather than 8 to 10 days. So that is the gist of what the osmotic system, rehydration system, and as vegetables start to lose water, because of the osmosis and the positive pressure, it's gonna constantly pull water back into the cell, and it's gonna keep the vegetable firm and rigid, and no decoloration, theoretically, no decoloration should take place within the vegetables. So that's the gist of the 2 inventions. And so I'll stop at this point and entertain any questions that you may have. Okay. I entertain any questions that you may have.
Okay, let me look. If y'all have any questions, you can unmute or you can type it up in the chat box. And we've got 2 people here that I think had some questions.
Okay.
Where do those insects go?
Where the insects go?
Do they come out the bottom?
What naturally, even when you harvest the vegetable, you're gonna pre-clean them. Today they pre-clean them essentially before you put them in a storage container. But by chance, if you don't pre-clean them, they're gonna still be in the container with the vegetables.
Okay, it's like,
but we know almost all vegetables, once you take them out of the storage container, you're gonna wash them, and you're gonna wash them before you cook them anyway.
Right. I guess I was thinking about blueberries and blackberries, which are typically harvested in the field and packaged and sent to a cooling center. Is this device meant to be used out in the field, like pulled behind a tractor, and as those items are packed, immediately put in there to cool them down as quick as possible? Is that what I'm understanding?
Now, with the first invention, you can actually essentially distribute, the containers within the field, and as you harvest them, you're gonna put them in that styrofoam container. You already got your ice wall, the ice cavity inserted into the top of the lid. So let's say, for instance, if you're doing sweet corn is a good example. And so with the first invention, if you already got the ice wall inserted into the lid, as you fill up your container, as you fill the container with sweet corn, you're gonna just simply close the lid, turn it over and close it, and water has already started to melt, and you just gonna close it, and water is gonna automatically start dripping down on that container. And now with the first invention, now, if you got a pickup truck or wherever, and you start stacking all your containers, so you get back to the storage shed. With the storage shed, you just simply start circulating water throughout the whole system, throughout those stacked containers. And going back to the first invention, once you stack them, you can insert a new ice cavity without unstacking the containers. I'm not certain what that now. And so with that container, now that was the first invention. So in the second invention, the storage container, you can just put them inside of that airtight chamber, the chamber where you're gonna raise the pressure and then lower the temperature. You can just put your container, the storage container, you can put it inside of that the airtight container for the osmotic system. And you could essentially, if you have a walk-in cooler, which they do have at supermarket, you just roll the whole thing in there. And when they run out of bunches of greens, sweet corn, you don't have to expose all the products. You don't have to expose all the product. You just take one box at a time, or whatever number of boxes you need. You just go to the supermarket, just go to the cooler and get a new box of sweet corn, and a new box that's filled with whatever kind of vegetables and fruits that you may have and stuff. Now, you may not want to do like blueberries, and maybe you don't want to, with the water, melted water, you may have a leaching problem. You don't want to leach out the juice of it. So it may not work that way with blueberries. Now, some vegetables is going to work well, some fruits and vegetables is going to work well, but others, it may not be suitable for that.
Okay.
Mm-hmm.
Right, but we had a comment here that you're not supposed to wash the blueberries, right before you eat them, and that is true. And the same with the blackberries.
Same with the blackberry.
Yeah, you just wash them before you eat them, but this would just cool them down.
This will just cool them down. Mm-hmm.
Yeah. Okay. Well, do we have any other questions from our audience? I know I'm going to call out on Linda Ham. She's one of our blueberry producers here. What do you think of this system?
Okay, got the unmute on.
There you go.
Yeah. It looked pretty interesting. Yeah, as you said, blueberries probably wouldn't, you don't want to get them wet, and they're pretty good keepers as far as getting, well, I go from mine to my refrigerator, and they keep for a month that way. I don't do store type of production, so I wouldn't know that area as well. And the rest of the people are just you pick. So I think I'm not quite fit for asking a whole lot of questions on that one. So, and then I freeze mine.
You freeze yours?
I do. I just take them directly from the field, and I don't wash them or anything because I don't use chemicals on my stuff. So yeah, I just put them right in the freezer bags and freeze them.
Okay.
And I pick clean. I'm a good picker.
Well, like I said earlier, it may not be applicable to all fruits and vegetables. Yeah.
Right.
But I know you don't want, like, as you said, certainly know better than I, that you don't want to wash the blueberries, when you harvest them from the field and stuff.
Mm-hmm.
Now,
and of course, if you put them in plastic bags within, watertight plastic bags, you can still reduce the heat real fast using this system. I mean, the cold water can run over the surface of the plastic bag. You're gonna still have conduction heat transfer.
Oh, yeah.
Mhm.
Yeah, I think your system was cool. I like it.
Okay.
All right. Next question, I guess, Dr. McGee, is I know this is a new invention and it's not out on the market yet. Do you know, are you doing some on-farm research, and do you know when this product might be released?
What
for
the next
farmers?
step, Colin, I'm trying to convince, the Office of Technology Transfer to give me some money to get prototypes made.
Okay.
So that's my next step, is try to get prototypes made. See, one thing about invention, getting an invention, well, if you got something unique and different, you can get a patent for it.
Right.
But when you run into, where you going to run into problem and getting prototypes made?
Mhm.
And a lot of folks think if you get an invention, folks gonna just well, folks think that the big commercial folks gonna knock your door down to get that product.
Mhm.
It doesn't work that way and stuff, because they know it's gonna knock some of their products off the market if they did that. But anyway, that's my next step, is to get some prototypes made. I'm gonna change some of the design factors, get some prototype made, and actually test them on the real life condition.
Okay.
Here at the university, because even at the Viticulture Center, we have a great research center, and they want to know, can we use this system for grapes, especially muscadine.
Mhm.
But see, I don't know what will happen if you absorbing all that salt, what will happen to the juice and the wine that you make from it.
Oh, yeah, that would affect the flavor, you would think.
That I would think that might affect the flavor. Yeah, but he was asking me, could you use it for that? So it may prolong the shelf life, but it's gonna have an impact on the flavor, I would think.
Yeah. We just had a comment about salt water on blueberries. Just doesn't sound good.
Salt water, well, and salt water on blueberry doesn't sound good, but I know some folks put salt on a watermelon when they eat it.
Oh, yeah, I do that.
Oh, okay.
Yeah.
And so if we store watermelons in this system, let's say you can store watermelon for 6 months.
Yeah.
Okay, with the osmosis, it's just gonna pull what? The saline solution in the rind part, and the flesh part still gonna be good.
Yeah. So the inside is not going to affect. It's just your
It's not gonna
outside.
affect. And
Yeah. So cantaloupes, because we have a lot of food safety issues with cantaloupes.
that's what I'm talking about.
Yeah.
What E. coli? Yeah.
As they get into
So-
those little grooves, and then when you go to cut them, that's usually when the spread of
That's what happened.
the bacteria.
Well, remember, with this system, we can use chlorinated gas, chlorine within the water. We can use chlorine, and the ozone gas will also kill E. coli as well.
Will salt water kill the E. coli or reduce it?
I'm not certain, buddy. I believe so. Well, I think salt water, I believe, will kill E. coli as well. But I know salt water will kill almost any type of bacteria. That's why we can we know in everyday life with salt pork, if you got that slab of salt pork,
Mhm.
if you got that layer of salt on the top of it, you don't have to refrigerate it. It may dry out on you. But as far as bacteria attacking it,
Mhm.
It's not gonna happen. You remember in the country stores when you go down there, those stores that used to sell those pig feet in the jars, boiled egg. You
Yeah.
didn't see any molds or fungus, any kind of growth inside of it because of that saline solution.
Okay. Yeah. Or lime. I've heard of the eggs being kept in lime water.
Yeah, the same thing.
Same thing.
That's what I'm talking about. That's a
Okay.
saline solution, and you don't have to refrigerate them.
Okay. Right.
But if they come above that saline solution, then you're gonna have a problem with, with molds and some other fungus, some other kind of growth and stuff. Yeah, we pickle stuff all the time, vegetables. Whether it's cucumber, okra, or like I said, even they used to sell those. I remember when I was a kid, you can go to the country store and you can buy that pick feet, and they just open the top and put a fork down there and wrap it in wax paper, and you on your way. And they were not refrigerated, and they could have been there for 6 months or maybe a year.
Yeah. This is true.
So
Things,
that's what
things
we're
you don't
talking
want to
about.
think about, but they're true.
Huh?
Things that you don't want to really think about, but they're true.
That's exactly right. So that's really what we are talking about with this system, essentially. So it is, you can use it to disinfect, or you can sanitize the product. And we in restaurants and stuff, and a lot of places, or food places where they use like ozone gas to sanitize the whole operation.
Yeah. Yeah. And that would be safer than the radiation.
That's
vegetables
exactly
and
right.
things like that. to
Even
kill
though
them.
radiation may
So-
kill the worms and insects, you're gonna have it's gonna be a hard sell to sell meat or whatever vegetable. And you say it's been what is it, gamma rays? If it's
Gamma-
been radiated, the public not gonna buy it if they know
Yeah.
that.
Yeah, I don't want that either. No.
Yeah, radiation back in the 60s and stuff, the 50s and 60s, they thought it was the panacea to all our problems in disinfecting and sanitizing fruits and vegetables and stuff, but that didn't work out so well.
Okay. All right. Well, does anybody else have any other questions? Regina, Robin?
No, but I sure did enjoy it.
Well, thank
I
you, Dean.
sure did enjoy this, Dr. McGee. This
All
has
right.
been really nice. I'm excited about the invention. I'm hoping that great things come from this.
Well, I think it would be a game changer in the post-harvest industry if it works the way that I have theorized that it's supposed to work. At least the patent folks thought it would work the way it's supposed to work.
Exactly. I wish
Because-
you nothing but success.
Okay, I appreciate it. Thank you too.
You're
Mhm.
welcome.
But so
Same
hopefully
here.
by next year, Carla, that we will have some prototypes made and we have tested the prototypes.
Okay.
And so I can have some more definitive answers, better answers to some of the questions. And we find out what vegetable will work. But I certainly think any vegetable with a protected shell, like sweet corn and peas and stuff, and the nuts family like pecans and any kind of nuts and stuff, even with peanuts, it should work very well, in my opinion. If like green peanuts, if you have already washed the peanuts and you store them in this system, as long as the salt get absorbed in the shell of the peanut, for folks like us, like me, who like boiled peanut, that's a good thing. You don't have to worry about putting in the salt in the water. You just open the bag and put water on them, because the salt is already in the shell itself.
Wow. That is, it just sounds like an amazing idea. I've enjoyed hearing about it, and I hope you do get those prototypes made, and we can meet up again next year and see, how this actually works in the field.
Yes.
We want to keep up with you on this research that you're doing.
Okay, and hopefully I can, like I said, get prototypes made, test the prototype, and ask the public to find it.
Okay.
And
Yes.
get it out to especially folks in the extension and stuff.
Right. And you can always, maybe through TSU research, we could cross state lines or something, and
Oh, yeah.
Yes.
bring it to Tennessee.
All right.
That's Regina.
Well, thank you all for inviting me.
All right. Well, thank you for being with us today. We really appreciate it. And I will get this video transferred to a YouTube video and send out, and then you all can share this information with those who were not available or able to be with us today.
So,
All right then.
All right, we're gonna close it out then. Thank you all.
Okay.
all right, bye-bye.